Shapiro start to work in knowledge representation. If you follow his publication, you can clearly see the orientation or the intention of his research is to address the whole field of artificial intelligence, rather than just settle down in one subfield of that, which I think distinguish his work from many other well-established AI researchers. So in a sense, that's exactly what we call AGI today, even though his work started long before this phrase was invented. Okay. And also his career or his research in this direction continues over many years, especially in the time when this kind of research is not fashionable in the community. So in that way, I think his work has established a very important, excellent role model for the younger generation of AGI researchers. So now let's welcome Professor Shapiro.
Thank you, Jay.
Great. Good morning. So some of this talk will be a repetition for the people who were here yesterday morning. I apologize for that. Well, not really, but there will be new material as well. And then if you want even more details, I'm giving a tutorial on Saturday morning, which again will have some different material in it. So I'll be talking about MGLAIR, modal grounded layered architecture with integrated reasoning. I want to thank my collaborators. Henry Hexmore first developed the GLAIR architecture as part of his PhD dissertation. And most recently, Jonathan Bona is developing and implementing the attachment of the M, the modal, to the GLAIR architecture. And Professor Anstey in our Department of Media Study collaborated on a lot of uses of this, and these other students also contributed to the development of GLAIR and MGLAIR. So this morning I'll discuss the motivations for GLAIR and MGLAIR. I'll show you some agents that we've developed, that we've implemented. Then I'll talk about the MGLAIR architecture and its layers, give you some introduction to the latest version of SNEPS, well, to SNEPS in general, which is our knowledge representation reasoning system, and I'll show you where that fits in, and then discuss some on symbol grounding, and then some on modalities in particular. So, as Pei said, I'm basically at heart a KR person, and the motivation for developing GLAIR and then MGLAIR was to add acting and sensing to a reasoning agent. And these agents that I and my group are interested in do first-person reasoning. And by that I mean that unlike other models of agents, formalized models. So I'm also a logic-oriented KR person, I should point out. And unlike other models of agents, the knowledge base, the collection of formulas represented in steps, is not taken to be a model of the agent, but rather the contents of the mind of the agent. So if the agent is not aware of something, then it's not an assertion in the knowledge base. And the other part is the acting and sensing is online. So rather than developing some plan for someone, it or a person or some other agent to carry out sometime in the future, it's acting as it's thinking. And I'll show you some of the constructs that go into that. The layers, again, this is a layered architecture, but I think it's different from a lot of other layered architectures. It's motivated by the connections among and distinctions between the mind and body. So this is my proposal for solving the mind-body problem. That sounds grandiose, but you'll see how it goes. But the layers are motivated by this mind-body connection. And we want to allow the same mind to be plugged into different bodies, which we've actually used, for example, in developing the upper layers of the architecture in a software simulation and later transferring it to an actual hardware robot. And it continues pretty much the same way. The interest in getting into acting and sensing by me, a KR person, is interest in the origins of sensation and the origins of beliefs in sensation and proprioception, and being aware, having first-person privileged knowledge of your own body. So how do you know you're sitting down right now? Well, because it's your body and you can feel it. It's sitting down. You don't have to reason about it. You just feel it. And another motivation is situatedness, having a sense of where in the world it is, where the agent is positioned in the world, and I'll show you a short example of how that plays out. And finally, an interest in symbol grounding, that is grounding the symbols in the uppermost layer with structures in the body. And thinking about what a symbol is, there's a lot of discussion on that. I see a symbol as a pivot between various modalities. I'll give you some sense of that as we go along. The motivations for adding modalities to GLAIR is that modalities are independent resources, independent of each other, yet each one limited on itself. And these resources are the sensors and effectors of the agent. So, as I said, different modalities can be used independently, but a single modality has limited use. That's essentially what defines a modality in the most general sense. So here are some agents. The first one developed with Henry Hexmore and other people. This is the hardware version of it, and it was called a FEVAR, Foveal Extravehicular Activity Helper Retriever, which we did for NASA. Hard to believe 20 years ago. Seems like yesterday. Well, that's a picture of it. This is a picture of it in the lab with these blocks representing people and other robots that it was dealing with, presumably on the space station. It's now sitting in a closet somewhere in Johnson Space Center. Anyway, this is a view of the FEVAR robot in a software simulation mode. And it's having a conversation with Bill, this guy here. And Bill says, "Who am I?" And Cassie, the FEVAR robot, says, "Your name is Bill and you're a person." So he knows something about Bill. Bill says, "Who are you?" And Cassie says, "I am the FEVAR and my name is Cassie." So, like good agents, it has a self-model. It knows some things about itself, including what its name is and what sort of being it is. And then Bill says, "Who have you talked to?" And she says, "I talked to Stu and I am talking to you." and that is vocalizing or putting into verbalizing into words a piece of her episodic memory. In order, in chronological order, I talked to Stu in the past tense, and I am talking to you present progressive. Now, a lot of the features of this little conversation have to do with deixis, in lexical terms. So she recognizes that when Bill says I, he means himself, Bill. She uses you in talking with Bill. She uses Stu, third person, to talk about Stu to Bill. And she knows that when Bill says you, it means her. So she responds about what's true about I. She uses I to refer to herself. And when I said that already. When talking to Stu, about Stu to Bill, she uses Stu. But talking about Bill to Bill, she uses you. None of those features are embedded in the knowledge representation. That is, what's represented in SNEPs are independent of these deictic characteristics. That plays a role in the analysis of language and the generation of language. So which term denotes the I, which the you, which term denoting a time is now and which is in the past, and the relation of now to durative actions is all part of translating her beliefs into language. This is another agent that was developed by John Santori as part of his dissertation. This is through the eyes of the agent wandering in this suite of rooms, being challenged to, as we put it, recognize indistinguishable objects. So one task was to count to count glasses in this suite of rooms. And the problem with that, of course, is you don't want to count the same glass twice, even though they all look alike and the rooms look very much alike. And in this other example, she's following a tour guide through this suite of rooms, and occasionally the tour guide goes through this room with other robots in it that look exactly like her, and the task is to figure out which one she's following versus the others. And he actually did some tests with people in a simulation to try to figure out how they did it and try to duplicate that in an agent. This is a Wampus World agent, again in the GLAIR architecture. The interesting thing about this particular problem, which is in fact solved, is for those of you who are familiar with the Wampus World, you should recognize that the agent, which is this green triangle in the upper left, is perceptually blocked from the goal. That is, in order to get to the gold, she has to go through dangerous cells. She tries to avoid this as much as possible, but eventually she can get bored and say, what the hell, I'll give it a try. And she managed to solve this problem. Then, as I mentioned, my work with Josephine Anstey, with a series of agents that were used as part of performances, plays, put on by UB's Intermedia Performance Studio. So Cassie is playing the role of these two tour guides in a virtual reality drama called The Trial, the Trail that Josephine wrote. Here also from The Trial, the Trail, these three guys here are harassing the participant who looks through VR goggles and is part of this VR world. And these three are all GLAIR agents. And one interesting thing about this is it's a multi-agent system, but each agent is completely independent of the others. They're aware of what the others are doing the same way they're aware of what the participant is doing through their senses. They have no internal access, no access to the internal minds of the other agents. It's all through the virtual world. This Jonathan Bona mainly implemented. These are two characters in a play written by Susie Laurie Parks that we put on in 2007. And it's a short play. It's scripted. And there are, I think, two participants and a light bulb. And an interesting thing with this is based on a suggestion of Josephine's. We did something that no one in the audience was aware of. Each agent spoke using TTS actually through a speaker, and the other agent used speech recognition through a microphone to understand it. No one was aware of that but us, but we still enjoyed the notion that these these software agents were actually speaking to each other through the world. Here are some agents that were part of another performance, and they just wandered around saying things. And so did these. These talked about a play that we were putting on. And Voyubu was a mashup, if you're familiar with, of two sort of avant-garde plays of the 1800s, Ubu Roy and Wojciech. And there's a war that goes on, a battle, and we use these Rovio robots to be the battle wagons, each of which was a GLAIR, run by a GLAIR agent. This wasn't a GLAIR agent at all, but I ran it, so I'm kind of fond of it. This is a bear that plays a role at some point in the picture. So it was a robot, and it had a green screen interaction with a couple of the players. And this is the delivery agent using Greenfoot software as the simulated world. And this, I'll get into the details of implementing this agent Saturday morning. So a top-level picture of the MGLAIR architecture. I generally talk about bottom to top, SAL to KL, but we're picturing it now as a circle with the world on the outside, and sensors over here and effectors over there, with arrows as the modalities. I'll sort of go through that in pieces. So what I still refer to as the bottom layer, it's the outermost layer, the Sensori-Actuator level, controls the sensors and effectors. So in a hardware robot, this is the onboard sensors and effectors of the robot. Then there's a set of layers called the Perceptuo-Motor Layer, and I'll talk about each of them, each of the sublayers in turn. PML-C abstracts the sensors and effectors and forms the agent's behavioral repertoire. And this layer is specific to the implementation of the body, whether it's a hardware robot or a software robot. PML-B handles translation and communication between the next higher level layer and PML-C. And this is the highest layer that knows the body implementation. So when we move the mind to a different body, we switch PML-B and below for a new PML-B and below, but with the same upper layers. The next layer is now divided into two parts as part of this move to MGLAIR from GLAIR. The PML-S, S for sensory, grounds the knowledge layer, the highest layer, symbols in perceptual structures, which I'll talk about some more as I go along. And this, with its companion, is the lowest layer that knows the KL terms. So PML-B and below are ignorant of the representation language that's used at the highest level. And these contain registers for embodiment and situatedness, including the deictic registers, which I showed you the use of in that FIVAR conversation, and modality registers. I'm not really going to talk about these much or at all anymore. PML-A is the other half of this sublayer. Again, it grounds the KL symbols, this time for the symbols of primitive actions. And again, it's the lowest layer that knows the KL terms and has these registers. Finally, the one that I tend to be most involved with is the knowledge layer, the upper layer, and that is implemented in the SNAPS KR system. It contains the agent's beliefs, that is not beliefs, third-person beliefs about the agent, but first-person beliefs of the agent, as well as beliefs of itself. The representation of conceived of entities. So if the agent conceives of some entity, it's represented at that level. Semantic memory, episodic memory, which I showed you a little of being verbalized. Quantified and conditional beliefs, that is, formulas expressed with quantifiers and connectives. Plans for non-primitive acts, which I'll discuss more as I go along. Plans to achieve goals. Again, I'll show you the constructs for this. Beliefs about the preconditions and effects of acts, which I'll talk more about. Policies, which are conditions for performing acts. I'll say more about that also. Self-knowledge and meta-knowledge. So that's all in the KL. Then there are afferent modalities that handle sensors. So they take sensations to what we call perceptual structures, to perception, to KL terms. And I'll say more about that. And then on the other side, efferent modalities, which go from KL primitive acts to implementations of them as PMLA methods or functions or procedures, to act impulses to the actual effectors. And again, I'll say a little more about that. So the knowledge layer is implemented in SNEPS, the latest version of which is SNEPS 2.8, although another PhD student is developing yet a more recent version, which, anyway. So this is a KR system, or KRR, knowledge representation and reasoning. Every non-atomic expression is simultaneously an expression of SNEPS logic, so it's logic-based, an assertional frame that is a construct with slots and fillers, so it's a frame-based system, at least assertional frames, and a node and a propositional graph, so it's also a graph-based system. And there are reasoning styles that accord to each one of these. But it's simultaneously all three. And an important aspect of SNEPS is that every well-formed expression is a term. So there are no well-formed expressions that are sentences in the standard logical view. And it's a term that denotes some mental entity, which I'll say more about. So let me say more about it. So here's the ontology of mental entities represented in SNEPS. So entity is the top of the ontology, and that includes propositions. And so a proposition is an element of the domain of this belief system. A proposition can be defined as something that an entity that an agent can believe or which it can believe the negation of. And this includes quantified and conditional beliefs, that is, what look like non-atomic formulas in first-order logic, but I'll show you some of those. Another category in the ontology is acts, and these are characterized by the fact that the agent can perform an act. Policies are condition action rules. These are neither believed nor believed. They're adopted or unadopted. Horrible word, but anyway. And everything else I'll just call a thing. This is the usual top of ontology, so everything else is there. These include actions, which is something that an entity that an agent can perform on sub-objects, as distinguished from an act, which is what an agent can perform. Categories or classes are elements in the domain. And other entities, including individuals, properties, times, everything else that an agent or you could conceive of. So, for example, here are some atomic propositions in the language that SNEPS uses. So the closest we come to in the syntax to just a proposition from propositional logic is a predicate with no arguments. It's not really a predicate. I'll say something more about that. And here are some examples. B4 has the proper name Stu. The height of B4 is 68, presumably inches. New York State is a populated place. 3.14 is a number. Oh, by the way, I know I'm swimming against the tide, but I insist on using ISA for the instance relation rather than the subcategory relation, because it's really based on sentences like, a dog is an animal, or Fido is an animal. And somehow Ron got the community off on using ISA for the subcategory relation, which, anyway. So I use a KO for a kind of. Although this isn't embedded in SNEPs, you're allowed to use different terms if you want for these relations. And here's a little piece of WordNet. So dog, whatever is the hypernym of dog is canine. Some non-atomic propositions. So I've always been concerned that the language that I'm using in the representation be capable of expressing English sentences as simply as the English sentences themselves. So I don't like taking a rather simple English sentence and formalizing it as a very complicated logical expression. Let me say also that although I believe in a logic-based KR, and I think that thinking is basically logical reasoning, remember that logic is not one thing. Logic is a study of correct reasoning, and there are many, 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 many logics, one of which is standard classical logic developed for metamathematics, which most people believe isn't good for developed for representing thinking and reasoning by intelligent agents. And my message there is, if you don't like one of the many, many, many logics that already exist, well, invent your own. So what I see as a basic task for KR is not an argument about whether logic is or is not right for KR, but rather what the correct logic is, or what the best logic is. May as well have more. I'm not interested in proving things about the logic, but using the logic for a reasoning agent. And so let's have a lot of connectives, whatever is useful and easiest. Not P, the conjunction of P1 through Pn, either in functional notation or infix notation. The disjunction of P1 through Pn, either in functional or infix notation. And note that the arguments of and or are really sets. Multiplicity doesn't matter, order doesn't matter, it's all the same. NAND, the NAND of a set of propositions, that is, they're not all true. The NOR of them, none of them are true. The exclusive OR, exactly one of them is true. By the way, when I say is true, I don't really mean is true. I mean the agent believes it, right? XOR, if and only if they all are believed or believed to be false, or their negation is believed more properly, and an infix version of this. Two generalizations of those are and or. So this takes a set of arguments and it says at least I and at most j of them are true for that interpretation of true. And thresh is the negation of and or, either fewer than I or more than j are correct. So there are instances of and or and thresh that aren't easily representable by any of the connectives that I showed you before. Some more non-atomic. These are the ones that I showed you are all symmetric about all its arguments. These take two groups. So these first two are just syntactic variations of if any of the P's are true or believed, then so is all of the consequence, or if the agent believes any of the antecedents, then the agent is justified in believing any or all of the consequence. This is what we call and entailment, which is that you need to believe all P1 through Pn to be justified in believing one of the consequence. Or if, not you need to, but if you do, then you are justified in believing a consequent. And this is a generalization. If the agent believes at least I of the antecedents, then it's justified in believing all the consequence. So the or entailment and entailment are special cases of the I entailment, of the numerical entailment. Quantifiers. So for all x1 through xn p, where p is any formula. And then 3 syntactic variations of what I call a numerical quantifier. The first says, of those x1 through xn that satisfy p1 through pn, n doesn't have to be the same, sorry about that. At least there are k that satisfy the p's, and at least I of them, and at most j of them also satisfy the q's. A special case is there are at most j x's of those that satisfy p that also satisfy q, like you have at most one biological mother. Then the other way around, at least I of the k things that satisfy the p's satisfy the q's. Reasoning. So it's not just KR, it's reasoning also. We use a natural deduction style of proof theory of derivations. That's typically characterized as having rules of inference for each of the connectives, introduction rules and elimination rules. Actually, Pelletier looked at lots of examples of natural deductions as the real characterization is that there are subproofs that one can go into and come out of. So as contrasted to SAT solving or resolution or other techniques for doing reasoning, natural deduction is more like what people do. It does forward, backward. So forward reasoning, give it a new thing to believe and have it draw conclusions. Backward inference, have a knowledge base, ask it a question, decides whether or not it's to say yes or not. Bidirectional goes in both ways. Focused, you could ask it a question and it might not get the answer, and then it can take new evidence and focus that evidence on the question at hand and ignore other things that one can draw from it. We retain derived formulas for later use, a kind of lemma using, so this can shorten later formulas, and is one thing we get out of natural deduction reasoning as opposed to various styles of refutation reasoning in which you start off assuming what you want to be true to be false, and then of course everything you derive from that is based on the fact that what you really want to be true is false, and so it's all, you have to throw it away when you're finished. It's based on the logic R of relevant entailment, which is paraconsistent, which means that it's not the case that a contradiction implies anything whatsoever. So it can use negation introduction, but only if the contradiction is relevantly based on what is being decided must be false. But it's not the case that you can just draw anything from a contradiction, which classical logic does. We have an ATMS-style belief revision or truth maintenance system. This can be used in a manual or, quote, assisted way where the system says to the user, assuming there's a user, oh, hey, I found this contradiction, and what do you want me to do about it? But it does guarantee, it does present possible culprits for the contradiction, and it's guaranteed by the logic that if you have it disbelieve any of the possible culprits, that contradiction will go away, at least in that way in which it was derived. It could be derived in another way also. Or it can do automatic belief revision. And a student, Ari, recently developed some of that. And that allows a user or an agent architect, when we're talking about agents, can specify an epistemic entrenchment ordering function which could look at two possible culprits and then call a function that decides which of them should be more believed than the other, more entrenched than the other, that is, which you should prefer to get rid of if it's a choice between these two. Okay, so let's talk some about acts. So that was all talking about the reasoning. but SNEPS is also an acting system, which is crucially used for developing agents. There are two ways of subcategorizing acts. One way is into external acts which affect the environment, and these must be supplied by the agent designer. Mental acts which affect beliefs in the knowledge layer, and these we've supplied, and they're believe and disbelieve for proposition-valued expressions, and adopt and unadopt for policies, for policy-valued expressions. And then there are control acts, including acts that represent a sequence of acts, a selection, a loop. So here we go, right? You all recognize that this is now a Turing-complete language. So we've got it covered. The second way of categorizing acts is primitive acts, and some of them are implemented as part of SNEPS, others are implemented by the agent architect in PML-A. So for any behaving entity, there must be some primitive set of acts that the agent can do without having to think about how it does it. It just does it. It's part of the basic repertoire. It can do it, but not analyze conceptually how it's done. Composite acts, which are structured by the control acts, and defined acts, which are defined by the proposition-valued expression. I'm not always going to continue saying that, but that's what I mean. Act plan alpha P, which means that the defined act alpha can be carried out by the act, now considered as a plan, P, where P is another act, hopefully more primitive, right? So it's often P is a structured one of these composite acts. So forming what some people call a hierarchical act decomposition. Yes. Here are some specific examples. These are propositions about acts that can be constructed in this representation language. Alpha has the precondition phi. That is, phi has to be believed by the agent for it to attempt to do the action alpha. You can see Strip's influence in these things. An act plan, which I just showed you, the act alpha can be carried out by performing the act alpha 2. Goal plan, if the agent wants phi to be true in its world, then alpha is a way to bring that about. An effect, the effect of, or an effect of performing alpha is that phi is now true in the world. Phi could be a negation, which means phi is no longer true, right? In fact, it's false. Then there are policies, which I've mentioned before, and policies are one way of connecting reasoning to acting. The first two are triggered by forward reasoning. When do phi alpha means that when the agent believes that phi holds, it is to perform alpha, and then unadopt this policy. Whenever do is whenever it believes that phi holds, it should perform alpha, and then it continues to have this policy adopted. The distinction, think about the policy of crossing a street by pushing a walk button, and then adopting the policy when the walk light comes on, walk across the street, right? You don't want to get across the street and say, oh, the walk light is still on, let me cross the street, right? I have to cross the street again, right? So that's a one-off, whereas whenever do is like whenever the fire alarm comes on, leave the building, and you don't want to unadopt that after using it just once. For backward reasoning is if you want to know whether to believe phi, then do alpha. So alpha is presumably a sensory act, which will tell the agent whether or not phi holds. Another set of constructs that connect acting with reasoning are some of the control acts. Some of these are based on Dijkstra's guarded statements. So sniff is a selection. Non-deterministically, if any of the phi hold are derivable, by reasoning, then perform non-deterministically one of the corresponding alphas. If none of the phe's can be derived, then do delta. Snitterate, if one of those phe's holds, do the alpha and then do the whole iterate again, the whole snitterate again. If none of them hold, then perform delta. Delta is an option. If that's not there, just go on, you're done. With some x that satisfies phi, perform alpha. But if there is no x that satisfies p, do delta, if that's included. So that's like the old example is put a quarter in your pocket into the parking meter. With a quarter that's in your pocket, put it in a parking meter. The challenge is formulate that rule in first order logic. You can't do it except by having two different quarters, right? If there's something in your pocket that's a quarter, take something in your pocket that's a quarter and put it in the meter. Could be it, right? Doesn't make sense. And then with all is with all x that satisfies phi, perform alpha. And if none do delta. Here are some control acts that don't connect propositions and acts. So achieve phi means for the agent to perform achieve p means that it will try to do something whose effect is phi, is that it believes phi holds. Do all non-deterministically does all those acts in a non-deterministic order. Do one does one of them non-deterministically chosen, and SN sequence does alpha 1 then alpha 2. So to make all this more concrete, here is the acting executive. I'll go through this, I think, semi-quickly. So to perform that act, first let, oops, better do this. First let P be the set of beliefs P such that it's derivable that a precondition of the act is P. So this triggers reasoning to do that. Then see which of these P's hold, that is, which the agent believes to hold, and set not yet to be the set that it doesn't believe holds. If not yet is not empty, then perform the sequence, do all A's such that A is achieve P where P is one of these not yet held, not yet believed preconditions. And after doing that, do the act, try the act again, which of course, if some of the preconditions have been undone by others, it'll try again. One problem that we have, I invite you to solve it, is we don't really take failure into account here. And there's got to be a way for the agent to decide that it's failed and quit and go on to something else. So if not yet is empty, now derive what it believes to be the effects of that act. If the act is primitive, then apply the PMLA primitive action functions to the objects. If it's not primitive, try to derive plans and then perform the do one of those plans. And finally, and this is quite naive, believe the effects. So in less naive agents, we don't tell it any effects, so it has to just sense what the effects are. But this is another obvious hole. It should know some effects and check that those hold. So now, a slightly different topic. So we need to discuss these three kinds of things. Objects in the world, such as us, terms represented in SNEPs in the knowledge layer, like B4, and then the issue of what those terms denote. Okay? And the standard answer is that these, doesn't always work, that these denote these. And that's not my answer. That's the extensional view of knowledge representation. My answer is that these denote these. That is, mental entities or intentional objects. And the agent uses these terms to think about these things. Right? There's no way to actually get out in the world and think about those things. Everything comes through our sensors, and it's all internal from there. So when you listen to someone else talk about something, right, like Fred or Stu, you will assume they're talking about what you mean by Fred or Stu, until you get into trouble, and then you'll have a discussion of, oh, you mean this, I mean that. Very seldom do we get into a discussion of, I say it's true, you say it's false, right? Most of the arguments are about our model of what it is we're talking about. So this is a fully intentional KR system. There's no extensionality. There's no denotation of things out in the world. Another way to view it is it's an extensional logic whose domain is the domain of intentional entities, rather than the domain of extensional entities. Alignment has to do with connecting the knowledge layer with objects in the world. So for afferent modalities, the agent starts with some object or phenomenon in the world, goes through sensing it, and then goes through perception, in which it interprets these sensations as representing things that it's conceived of or conceives of in order to understand what's out there. And on the efferent side, there are actions that bottom out in primitive actions that are implemented by PMLA methods, which cause action to occur in the world. So let me talk about the symbol grounding issue a little more, and this was especially used in the FIVAR agent, less so more recently. So I still believe it. We just haven't gotten around to working on other things. So here's an example of something out in the world, me, and there are some cameras that do sensing. And then the internal structure is some n-tuple of values on various dimensions. So a height, a width, a texture, weight, whatever. Okay, so that's from the world through SAL to PML. And then a connection of the PML structures to KL terms. So in KL, there could be this proposition, a proposition valued expression, that the proper name of B4 is Stu, where B4 is aligned to this PMLS structure, i.e. the agent, in a sense, knows what Stu looks like. That is, if it senses this PML structure, it can interpret that as B4, and if it needs to find B4, it can direct its sensors to look for something that satisfies that structure. Now, those were complete PML structures. One could also have incomplete PML structures. So, for example, if the agent believes that the height of B4 is B12, then B4 can be aligned to a PML-S structure in which only the dimension of height has some value to it. So anything that looks that high will have a structure like this. And PML structures can be unified. So here's a KL term B6. It's a member of this category B20, and the category B20 is aligned with some way that those things look, right? A partial PMLS structure. B6 has a property B30, which looks like this, and another property B31, which looks like this. So here, there's a knowledge there's in a sense a description of B6, right? The agent believes that it's this kind of category with these kinds of properties, and the category and the property are both perceivable. Okay? And so one can unify these PMLS structures to get a complete or more complete PMLS structure. That is, this guy looks like that. Right? If there's just a complete PMLS structure, but none of the properties or categories of the individual have partial PMLS structures, then that's a case of the agent being able to recognize B6, but not being able to verbalize what it looks like. Right? Your face looks familiar, but I don't know how I recognize it. By the way, let me throw this out. If you want, we could discuss it. I think this is the answer to what qualia are. That is, red, that's what it looks like. I can't explain it any further. That's what red looks like. You might have a different PMLS structure for what you call red, and you and I may agree on the set of things we call red, but there's no way that we can analyze this structure because this is not part of GLAIR. And so we can't think about it, talk about it, conceptualizing it. We can think, talk, and conceptualize about this, but not about that. That's just the way it looks. Can't explain it any further. Okay, finally, modalities. So John Bona is going to defend his thesis within a week after I get back on the development of the M part of MGLAIR. So he says a modality is a 9-tuple. I really hate that way of defining things. If this comes second instead of third, does that make it something different? Anyway, so there's a name for the modality, a type which is afferent or efferent or some subclass of those, some predicates that it uses at the KL level, a data channel because PMLB and above could be running on one machine and PMLC and below on another machine in a different language, and they have to communicate. We've actually done that. Some access rules, which I'll say a little more about, a focus level, which I'll say a little more about, a conflict handling method, just a comment human readable description, and some relations to other modalities, which I won't talk about. The modalities also contain buffers. The efferent modality buffers reside sort of in the PMLB of efferent modalities. They have a fixed capacity or an expiration interval after which things go away. When a new act impulse is queued, is put on the buffer, it's either queued at the end or it replaces an old impulse if they can't both fit. So that's an issue of being a limited resource. When an impulse arrives that can't fit, the conflict handler determines what's to be done. One possibility is ignore the new thing. The other possibility is discard from the buffer the oldest thing in it. Now, if an impulse is discarded from the buffer, then it's never performed. Impulses that are in the buffer are removed by a buffer management process and then processed in the PMLC and therefore done. On the other side, in perceptual buffers, these also are in the PMLB, sort of. Again, they queue perceptual structures, that is sensory data. Again, they have fixed capacity or an expiration interval. When a structure arrives that can't fit, either it or the oldest structure in the buffer is discarded, depending on the conflict handler. And discarded structures are never perceived, right? Because they get thrown out from the buffer before the perceptual functions operate on them. So they're sensed but not perceived. Think gorilla in that, passing the basketball for those of you who have seen it. And then structures that remain are removed from the buffer by a buffer management process and given to a perceptual function to be perceived. Focus, which is part of the modalities, is mainly relevant to afferent modalities. So the focus level affects the frequency of execution of the internal processes that manage the modality. It could be as low as just ignore this modality totally or maximally focus on it. Initially, it's at the default setting that the agent architect specifies when defining the modality. The agent might or might not be permitted to consciously adjust the focus of one of its modalities. And of course, the agent might not perceive phenomena in low-focused modalities, because before they get processed, they'll get replaced by something else, by other senses. And so it's important for the agent architect to adjust the relative focus of different modalities appropriately, or they'll allow the agent to do it. So think watching the road versus talking on your cell phone, right? If you're focused totally on the cell phone, then you'll crash, right? Or you can focus totally on the road and ignore the person on the other end of the phone call. So, to summarize, MGLAIR adds acting and sensing to reasoning agents. The layers capture the mind-body distinction and the mind-body connection. Modalities are independent of each other, but each limited resource for acting and sensing. SNEPS has, I claim, natural constructs for reasoning and acting. The modality buffers cue act impulses and afferent structures, but discard ones that are not processed. And the focus level determines how much a modality is ignored. So for more information, you're welcome to tune in on Saturday morning or consult our web pages. And there's a whole bibliography and lists of talks and so on you can find there, as well as software that can be downloaded. Thank you. Tom? Oh.
Well, I'm loud. I'm curious about, I'm going to, of course, ask a probability question, or at least an uncertainty question.
Okay.
So maybe how do you handle the case where you, well, a classic one would be sort of tracking radar blips, but let's say there are 2 or 3 people in a crowd and one of them is Stu, and our agent is not sure which one it is. So how do you see it as it gathers more information, resolving its uncertainty about that?
Okay. So I recognize that's an important issue, but I'm incapable of dealing with it myself. So what I've often told people who say, why don't you add uncertainties in probabilistic reasoning? I say, great, you do it. I'm perfectly happy to let you do it and modify SNEPs appropriately, but no one is bit yet. So it's another one of the things that is on the to-do list to make this a more perfect agent. That's all. That's all I can say. You're welcome to do it.
Oh, it's a separate question, so maybe Paul will ask me.
Thanks. Hi. Makes it very loud. I was wondering about the status of things like learning in this architecture. I can see one form of obvious learning, which is some kind of belief updating. Is that the scope of what you anticipate, or do you see reinforcement learning or concept formation or other kinds of things going on within this kind of an architecture?
Yeah, I always have to remember when I respond about learning that it does some learning. It does learning by being told, which is a not very exciting kind of learning. And it does learning in the sense of these lemmas, right? So it can get more efficient about reasoning as it's reasoned. The focus reasoning actually allows it to become an expert, to transfer in certain ways book learning into practical rules. There's really a technical explanation for that, which I won't get into. But most of what you mean by learning, I have the same answer as what I gave Tom. That is, I recognize it's important, but I can't do that too, and none of my students have assessed to go into that. So again, I welcome that kind of addition to the whole project, but I can't do everything.
So can you say something about memory management? I see on the, you have input buffers for sensory and oops. Oh. But what about sort of episodic memory and forgetting?
Yeah,
Is
right.
the agent reason about that also?
Oh, you guys are focusing in on the list. So every once in a while, I tell my students, someone should work on forgetting. I think one person did for a little while, but it somehow wasn't complete enough to really incorporate it. Yeah, forgetting is another obvious thing that should get added, but we just haven't gotten around to it.
So maybe another question. So I really liked your analysis of alignment, as you call it, I guess.
Uh-huh.
What are some of the objections to that, or maybe someone else in the room can raise them? I'm curious about that.
I haven't heard them yet. Maybe someone in the room will toss some in. There certainly are different approaches to alignment. I mean, there was a whole issue of, I think it was robotics and autonomous systems on symbol anchoring. And so there are other approaches, but I haven't gotten into discussions about what's wrong with this.
Good morning. You said some interesting things about
Where-
focused.
Who's talking?
Good morning.
Oh, okay.
You said
Okay.
some interesting things about focused reasoning. In communicating agents as opposed to perceptual, have you looked into ways that agents can focus their attention in terms of conversation, reasoning, reading, analysis of text corpora?
Well, these are communicating agents. The FIVAR agent I showed you communicating in a restricted subset of English, and we have built other agents like that. We haven't done too much of it lately. My students convinced me that the way I was implementing natural language parsing and generation was getting outdated, and I said, well, substitute something else. I'm doing something a little different right now in analyzing English intelligence messages, but I'm not really fully sold on
Would you call
what
the
it is
knowledge
that I'm doing.
representation in this ontology driven?
Say that again?
Would you call the your approach to knowledge representation and these description logics, or where description logics can be used, ontology driven?
Okay, so my approach is not ontology driven. I believe that people don't really have a deep notion of ontology. If you ask someone what they mean by almost any word they use, they will quickly stop being able to answer. And I was at too many meetings when the ontology movement was getting started in which people argued about what it was that ontology meant. And I figured if you can't even agree on that, how can you ever agree on what the specifics of the ontology are? And of course, every ontology developer has a different top-level ontology. They can't agree on that. I supervised one dissertation on ontologies, but it was ontology mediation, under the belief that different people will build different ontologies, and the problem is understanding what terms in one ontology correspond to what terms in the other. I don't believe in what I nastily call the fascistic approach to ontology development, which is, I'm right, you all follow what I say. So it can represent, as I showed you, category hierarchies, that is, ontologies, but I don't get into deep issues about the development of ontologies per se. Oh.
Thanks, Stuart. I had two questions actually. One was just a quick technical one. You were saying you're doing, with the KR stuff, you were using natural reduction, and then you were storing all of your intermediate sort of theorems. Does that lead to a large explosion in the, say, the size of the knowledge base?
To some extent. To some extent. And so here's another task that I've tried to get some student to worry about. And that is, it's related to forgetting when is a lemma worth keeping. So it must, I think, have something to do with the amount of effort to derive it versus how generally useful it seems. And so I would like to have some kind of system that judiciously saves some lemmas and not others. There are some that are very useful, as I mentioned. You can have universally quantified statements that have universally quantified statements in their scope. For example, the definition of transitivity. For all R, if R is transitive, then the transitivity rule. And apply that to some particular relation and say, oh, I know this relation is transitive, right, like bigger, therefore if x is bigger than y and y is bigger than z, x is bigger than z. And then the system saves that. And as a result of another dissertation by Jungming Choi, when it goes to reason, it uses that and completely shadows the more general case. And so then it's reasoning about bigger, even though the knowledge base has more things in it. It's reasoning about instances of bigger is actually faster than it was before because it doesn't have to use the more general rule. So that's a real win for this notion of saving lemmas. But in a lot of cases, the lemmas are specific ground assertions, and it hardly seems worth it at those times.
Okay, cool. Sorry, just another question as well. Do you represent any kind of notion of concept, or because you were saying, I think before, that your sort of mental entities are expressions of some sort.
Okay, thanks for asking that. Let me try to clarify. First of all, I don't like using the word concept because I find whenever I do, people misinterpret me. Okay, I've been present at a lot of philosophical discussions about concepts and what they are, and I think they get it wrong. Mental entities are represented in the knowledge base. They are not terms of the knowledge base. So mental entities are what the terms denote. And every well-formed expression is a term, even those that denote propositions, because we can talk about propositions as well as anything else. So my notion of mental entities is close to what people mean by concepts, but then they get to talking about, well, if there's a concept, it's a concept of, and what's the relation of a concept to the thing it is a concept of, and no. I mean, these are terms in the language of thought, if you will, and they denote and represent and are used to reason about these mental entities, which are the things we think about. And that's the story, and I'd rather avoid concept talk.
Thank you, Professor Shapiro. I have a question concerning your short comment on qualia. You mentioned it. Well, because I study philosophy.
Okay.
Your idea looks like that, if my understanding is right. You believe that different agents, they have different ontologies. And when different agents perceive the external world, their ontology will underlies their perception, but they have not the mental capacity to reflect upon or express their own ontology. So that is an unspeakable aspect of the perception. So you call it qualia, is right?
No, it's not the ontology. It's the PML structures.
PML structure.
Okay, so that is that there's the structure, which is the ultimate product of the senses. And then there's this method, routine, procedure, function, what have you, that recognizes sensations, that is, recognizes what conceptual, there I've used a variation of the term, entities these are, or cognizes, and, I've never seen one of these before, so I'll construct a mental entity which is that thing that I'm looking at, and then there's an alignment of that with a PML structure. And it's the PML structures that I think, but I'm not ready to defend in writing because there's a vast literature on qualia, and I would have to address point by point how this solves that problem.
Yeah.
But it seems to me that that's what people mean when they talk about qualia. That is, my example of red, right? I mean, it's what, to me, red looks like. But since this is a sensation, I can't describe it in words because it's not conceptualized. It's not part of KL. And we've taken agents that where the top level is the same but use different PMLS structures for the same things in the world. And so we have had examples of two agents or two versions of the same agent that have the same KL terms, think about the same entities, but their sensations are different, but the sensations are all triggered by the same phenomena in the world. And so it seems to me these two agents are in exactly this issue of qualia being such that you can replace them all by different ones, but if you do it consistently, you can't, no agent can tell.
So my response is, if that Chalmers and Nader-Brock, those philosophers have heard of that, they would respond in this way. But even if that's true, but it's irrelevant to the qualia talked by philosophers, they will think about a possibility. Is it possible to design a super agent which can reflect upon its own PLM structure? So if we can get it on the objective level, so we can convert qualia onto something from the third personal perspective. But by definition, what philosophers mean qualia is something purely subjective.
Well, so it's subjective in the sense that it's what the agent takes to be red, or whatever, square, right? But there's no objective way of comparing it with that structure of any other agent because they don't have access to their sensors, right? And so an interesting notion is one could build an agent who is a cognitive scientist or philosopher, philosophizing about their own qualia and forming theories of it, but they can never know that they're correct because they don't have conscious access to the PML structures. So they can model it, they can do experiments, they can form theories of it, but there's no way that they can actually know that they're correct because they don't have access at the KL level to those structures. They just have access at the KL level to the KL interpretation, perception of those structures.
But is that a conceptual impossibility or just empirical impossibility? That means it is logically impossible to have access to that structure, or just empirically impossible?
Well, it seems that's empirically the case among people. And we designed the system to have alignment the way it is before I thought, oh, those look like qualia. So I would say it's an empirical result, and that's what I'm interested in, right? Building human-level agents, and that seems to accord. But I haven't, and you're welcome to, to do this. I haven't sat down with all the vast literature and say, here's how this agent architecture satisfies or contradicts this theory of what qualia are. So right now it's just a suggestion.
Yeah, thank you very much.
I'd like to understand better the communication between the layers and the constraints or not that are involved. So my question is, to make it very practical, for example, can a inner layer put a action into the action buffer, or into the effluent buffer, I think you call it?
Efferent.
Yeah, so actions that are outgoing. Does it have to be a fully realized action that outer layer can perform by itself, or can it be a placeholder action that says, okay, when I get to the front of the queue, call back to the inner layer and then I'll tell you what to do? You know, producing kind of loops within the layers.
Yeah, the way we have it, those composite acts are composite at the KL, at the knowledge layer. What you make me think of in talking about lower layers actually putting impulses in efferent buffers are things like reflexes. Right, so a reflex somehow happens between sensation and acting without the participation of the knowledge layer, right? That's what reflexes are. Although the knowledge layer can affect a reflex. So you can stick your hand in a flame if you really want to, even though your reflex would have you pull it out. Or you don't always, when you bump into something, back off from it as a reflex if you actually want to push it or push the door open, right? You have to contact it and push, you don't just back off. I think that's a very interesting aspect of reflexes, that there is some control that can be exerted on them from the top, even though they mostly operate, from sensor nerves to the spine and then right back out again without going up. And again, not yet done by us.
No more questions? Okay, in that case, let's thank the speaker again for this wonderful discussion.